Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In a previous video, I showed a very close relationship between symmetries defined by a one-parameter group of transformations and the notion of vector fields and hence their associated differential operators. This naturally raises the question, well, what about more general groups of symmetries? Well, to consider that, we need to generalize the notion to the notion of a Lie group. And a Lie group is essentially a type of infinite group which can be studied using differential means. Okay, so let's turn to the definition for what a Lie group is. So what is a Lie group? So firstly, it is essentially just a group which is simultaneously a manifold, and those two structures are compatible with each other. So we start with a manifold G. We also have a group multiplication, which I'll call mu, which is essentially a map from G cross G to G. Okay, you're combining pairs of elements in the group, ordered pairs, to give you a new element in the group. And then you want compatibility between the two. So what does compatibility mean in this case? Well, firstly, you have this map here from mu from G cross G to G. And remember, G is a manifold, so G cross G is also a manifold, and you can ask if this is smooth. So the first thing you want is that this map is going to be smooth. So the other thing that you have is, of course, since it's a group, you can also define an inverse map from G to G. Okay, so that's an automorphism. It sends every element G, little g, inside this group G to its inverse. Okay, and so since you have a map between manifolds, you can ask whether that is smooth, and that's the second axiom that you want to have a Lie group. Okay, so that's the definition of a Lie group. It's simple enough. It's essentially a group with a manifold structure, and those two are compatible in the sense that the group multiplication is smooth, and also the inverse map that you naturally have from a group is also smooth. Okay, so let's look at some very important and natural examples, simple examples. So of course, the first example is R itself. So that was the one that we used when we wanted to study a one-parameter group of transformations. More generally, we can look at R to the n. Okay, so R to the n, it's an additive group. Okay, and it's also clearly a manifold. That's how you base all manifold theory, is on R to the n. And now let's just check that the group addition, and so this is an abelian group, so the multiplication is addition, and the inverse is negation. Let's check that these are indeed smooth. So if you add an n tuple xi to an n tuple yi, the ith coordinate of that is just xi plus yi. Okay, that's the ith coordinate. And of course, this is a smooth function of the inputs xi's and yi's. So this is a smooth map. The group addition is smooth. Similarly, the group inverse here is negation, and that just sends this n tuple with coordinates xi to the n tuple with coordinates minus xi. And so you're just negating all of these, so that again is smooth. And there you have it. This Rn is a Lie group. Okay, so let's do a more interesting example, and also one that's extremely important, and one that is non-commutative, okay, in general. We're going to have a look here at GLNR. If you haven't seen this before, okay, you might have seen this in a group theory course, since it is a very natural group to look at, okay. They're basically the set of n by n matrices, okay, which are invertible. Okay, so they're just that set. So it's a set of n by n matrices. Any n by n matrix is of course just given by an n squared array of numbers. Okay, so the space of these is naturally R to the n times n. Okay, it's naturally an n squared dimensional Euclidean space, and this is just going to be some subspace of that. And in fact, it's an open subspace because basically it consists of all of those matrices where the determinant is non-zero. Okay, so this determinant non-zero is an open condition. So it's actually, this is actually an open submanifold of Euclidean space. Okay, so here we have something which is both simultaneously a group. Okay, you can multiply two invertible n by n matrices to get an invertible n by n matrix. Okay, and of course the inverse is also an invertible n by n matrix. Okay, so that gives you the group structure, and it's also a manifold, being an open submanifold of this. And then to check that it's a Lie group, you just have to check compatibility of these two structures. Okay, so let's do that. So we need to check the group multiplication of these two invertible matrices is actually smooth. So let's have a look here. So let's look at the matrix whose ijth entry is Arj, and another matrix Bjk, the jkth entry is Bjk. So what is the product of these two? Okay, so the easiest way to write that is to look at the ikth entry of that. And the ikth entry of that, I wrote it so that the indices make it easy to write. Okay. What you do is you look at the ijth entry of aij times bjk, and you look at this for all j equals 1 up to n, and you take the sum. Okay, so this is the familiar formula that you know, and the key point is that if you look at this expression, okay, is this a smooth map? Okay, so you can see here that all these entries, they depend smoothly on the inputs. Okay, it's just a polynomial expression, okay, in the inputs. Okay, so this group multiplication is indeed smooth. Okay, so that's the first axiom. So the other axiom that you need to check is the inverse map. Okay, and that's why we like to use Cramer's rule. So Cramer's rule is not a very effective way for computing the inverse, but it's a very good part of the theory because it allows us to show, for example, straight away that it's smooth. Because Cramer's rule tells you that if you want to invert a matrix like that, what you need to do, you just look at the adjoint matrix. Okay, and so the adjoint matrix, of course, the entries of those are just polynomials in the entries of the original matrix. Okay, so that's very, very easy to see that's smooth because they're just polynomials. And then you have to divide by the determinant, which is non-zero. And the determinant is also a polynomial function, so you're dividing by a smooth function whenever it's non-zero. So that's going to be a smooth function. It's essentially just a rational function of these, okay? And it's well defined. So that's why the inverse is also smooth. And that shows you that this GLNR is a Lie group as well. Okay, so let me just talk about a slightly different version of this, a variant of this definition, and that's GLNC. That occurs with this example here, GLNC. Okay, this is essentially the same example here, except for you change the reals over to the complexes. So the set of all invertible n by n complex matrices. Now, if you look at that, you can see that similarly, well, here's the multiplication formula. This is also a smooth map, okay? Inside here will be inside C to the n by n, okay? So that's going to be complex space, so it's also going to be a submanifold. And you have the same formula for the inverse, and that's also smooth, so it is a Lie group. But actually, you can say a little bit more, because in fact, C to the n cross n, that's a complex manifold. So that it has holomorphic structure. And it's an open subset inside there, okay? So in fact, it's going to be a complex manifold, this. And not only is mu and the inverse, not only are they smooth maps, they're actually holomorphic maps as well, okay? So in this case, when you look at the G cross G, this cross itself, that's also a complex manifold, and you can ask whether the multiplication is holomorphic. And of course, it's polynomial, okay, the multiplication. And here, the inverse is given by a rational function. So it's holomorphic as well. So in that case, we call it a complex Lie group because it is simultaneously a complex manifold and a group, and they're compatible in the sense that the multiplication and inverse are actually holomorphic maps. Okay, so how do we come up with extra examples? So as usual in mathematics, we look at the notion of subobjects. Okay, and I guess the notion of a subgroup is easy enough. Okay, the notion of a submanifold is a little bit more complicated. Okay, so I don't want to go to the more complicated version. I'll just keep with the simple examples, which will give us lots of interesting examples and the most important ones in Lie theory anyway. Okay, so the notion of a Lie subgroup. Okay, I won't go through the general notion, but here is the simple version. Okay, suppose you have a Lie group G and you have a subgroup H, okay? Then if this subgroup, you want to ask, is it also a Lie group, okay? Well, suppose it's an embedded submanifold. If it's an embedded submanifold, in particular, it's a manifold as well, and you can ask if the restricted multiplication here, okay, is also makes this submanifold a Lie group. And of course, if you just restrict this multiplication to some subset, okay, it's going to be smooth, okay? And since H is a submanifold here, okay, an embedded submanifold, okay, that map there is also smooth. Okay, so in that case, you can also check that the inverse is smooth. So in this case, you'll find that you will get a Lie group. Okay, the restriction of the multiplication to this subgroup, okay, is in fact going to make it a Lie group. The notion of an immersed submanifold, which is also a subgroup, okay, that's a little bit more complicated. They do exist, this notion of an immersed Lie subgroup, but I'm not going to talk about it today. Okay, so let's have a look at some important examples. And the following one here is very important, okay? The unitary group of n by n matrices, n by n unitary matrices, okay? And this is going to be a Lie subgroup of this GLNC that I've put here, okay? So this is a complex Lie group, and this is going to be just a Lie subgroup, a real Lie subgroup, not a complex Lie subgroup, okay? And what it's going to consist of is just the unitary matrices inside here. Okay, so what are the unitary ones? They're the ones where the inverse is given by the adjoint. Or in other words, the adjoint of A times A is just equal to the identity. Okay? So that's going to be what you want. Okay, the set of these matrices inside here. Of course, this automatically tells you that A is invertible, so I don't need to include anything else there. Okay? So let's just check to make sure it's a subgroup and it's also an embedded submanifold. Okay, and how do we do that? Well, for the subgroup, you just need to check that it's closed under multiplication, okay, and under inverses, and it contains the identity, and that's quite easy to do. So I'll leave that for you to check, and it just comes from just looking at this equation here, okay? So that's very, very easy to do. So the more interesting thing is to show that this is actually a submanifold, because even if you do some manifold theory, okay, usually you don't get to see these types of examples. So I thought it would be nice to illustrate what is going on in this particular case. Okay, so what's the easiest way to check that something is a submanifold? Well, in this particular case, we're going to use the implicit function theorem. Okay, so what's the implicit function theorem? How does that work? So let me just show you more or less what's going on. Okay, so for the implicit function theorem, we start with a function. Okay, so we're going to consider H is my function, and the domain is going to be the set of n by n complex matrices, and I'm going to map it over to the set of n by n Hermitian matrices. Okay, so what do I mean by Hermitian? Hermitian means that the adjoint is the same as itself. Okay, it's self-adjoint. So B star is equal to B. All these n by n complex matrices where B star equals B. So how am I going to map from A to here? Okay, what I'm going to do is I'm going to look at A star times A. Okay, so you have this n by n matrix, and you multiply these two n by n matrices. Of course, you get some n by n matrix. And I claim this is, of course, Hermitian, and hopefully you can see that straight away. If you take the adjoint of this, you've got to multiply the adjoints, but you do the adjoint of this, which is A star, times the adjoint of this, which is A. Okay, so it's just A star A. Okay, so this is actually Hermitian, and that's something that you have. Okay, you have a map from this n squared dimensional over the complex numbers n squared dimensional space to this space over here, which is, well, it's smaller dimensional. And why have I chosen this one here? Okay, so the point is that what is the set of unitary matrices? Okay, it's just basically the solutions A to this equation. Solutions inside GLNC, or more generally inside MNC, if you like. So basically, it's just the inverse image of the identity matrix here. The identity matrix is Hermitian, and if you look at all the things which H maps to the identity, that's precisely this subgroup of unitary matrices. Okay, and the key point is that this implicit function theorem tells you when inverse images of maps between manifolds is indeed going to give you a submanifold. Okay, it gives you a criterion for that. Okay, so the first thing to note is, of course, this is actually just a Euclidean space over R, a real Euclidean space. So this is the manifold. Okay, and the thing that you need to check. Okay, let me just see if you haven't seen this before. Okay, the thing you need to check is just that the derivative of this map here, DHA, is actually surjective for matrices A in UN. Okay, so that's what you need to do. The derivative at A is going to be surjective as you vary A for any A inside this fiber, this inverse image. Okay, so let's just see how that works. And I don't want to prove that formally. I want to give you the intuition, although you can turn this into a formal proof if you want. Okay, so basically what do you do? Okay, so kind of how do you get a sense for what's going on here to see surjectivity of this? Okay, so firstly, what are the tangent spaces here? So this is a Euclidean space, this is a Euclidean space, so the tangent space is the same as itself, okay? So basically, the tangent space here is just a space of n by n complex matrices. And we can vary by a little tangent vector, so we'll vary by some small matrix, some delta A, okay? And we see what happens, okay? So basically, what is the derivative? The derivative is the linearization of this map. Okay, so what we do is we make some small variation at A. So we're looking at DH at A. So we start with A as the input for this map, and then we vary by this delta A. So we look at A plus delta A star, adjoint, times A plus delta A. And we see what that corresponds to. Okay, so let's just see what it is up to first order. So you get A star times A. Okay, we just star both of these. So it's A star plus delta A star. And then we get A star times A, and A star times A. A is inside the unitary group, so this is just the identity. And then you get this delta A star times A. Okay, delta A star times A. And you'll get this A star times delta A. And then the last term you'll get is delta A star times delta A. And as usual, when you're computing derivatives, okay, this is a second order term, so you can approximate that to 0, okay, in this calculation, because we're only interested in determining the derivative, okay? So it's this change, that's what we're interested in, okay? And basically what we're trying to do is we're trying to say that this change, you can hit, this is basically the tangent vector, you can hit any Hermitian matrix you like. Okay, so let's just rewrite this in a sense that you can actually see what's going on. Okay, so firstly, here's your I, and I'm going to write this in a very funny sort of a way like this, okay? It's going to be, so let's look at this thing inside the brackets here. So you have delta A times this A star, and then we're going to add to that its Hermitian conjugate, so it's an adjoint. So we conjugate that, or adjoint that, delta A times A star, that's the same thing as here, and we adjoint that. And then we're going to apply this conjugation. Okay, so A star, remember, is the inverse of A. A is unitary. A star times this times A. Okay. So basically you want to say that it doesn't matter what a delta A you can kind of pick, okay. You can get all sorts of Hermitian matrices here. Okay. Now this A star and this A, they're invertible, so at the end of the day, it will turn out that what you need to do is you need to show that you can get any Hermitian matrix inside here. Okay. Now this is Hermitian because it's a matrix plus its adjoint. And for the same reason as this, or very similar, okay, this is Hermitian. If you take the adjoint of this, you get just this inside here. The adjoint will remove that star, and then you get adjoint of this. So it swaps these two summands, okay, when you take the adjoint of this. So this is Hermitian, okay. So what else do you have? So what is this factor here? So delta A can be any matrix here, n by n complex matrix, and you multiply it by this invertible element here. So as delta A ranges over all of this, delta A times A star ranges over all possible n by n complex matrices. So you're saying as you range over all possible n by n complex matrices, and you add that to its adjoint, okay, it's quite easy to see that you range over all Hermitian matrix. Any Hermitian matrix can be written as a sum of a matrix and submatrix and its adjoint. In fact, what you can do is you can add, you can write it as half. If you take a Hermitian matrix and you halve it, okay, you can take that half. Its adjoint, since its Hermitian, is the same, so you add also another half here, and you'll get that original Hermitian matrix. Okay. In any case, that's roughly how that works. I'll let you think through the details, but this is a rather interesting application of the implicit function theorem, okay, which gives you lots of interesting examples of submanifolds. And they're interesting because they also are very useful in studying symmetry. Okay. So at the end of the day, what we've proved here is that using the implicit function theorem, this is also a submanifold, okay, an embedded submanifold, and so this is actually a Lie subgroup and hence a Lie group. Okay, let me just give you two more very important examples. So inside here, you can just look at the matrices here which have determinant 1. Now, since it's unitary, hopefully you know that the determinant has to be some complex number of modulus 1, okay? But it might not be 1. So if we throw in the extra condition, the determinant is 1, then we will get a subgroup, okay? And it's also a submanifold, embedded submanifold. So SUN is just all the unitary matrices A inside UN with determinant 1. Okay, so it's clearly a subgroup, and you can show it's a submanifold by applying this implicit function theorem again. You can look at the determinant map, and then basically, so the map from UN to R, you can look at that determinant map, and basically this will be the subset where the determinant is 1, okay, and then you apply this implicit function theorem again to show that it's a Lie subgroup. And similar techniques also show this slight real variant of it. So we can look at, so the S here always stands for special, which means determinant 1. So instead of looking at SUN, you can look at SON, which is the special orthogonal group. The N here refers to N by N, so that's just basically the set of all N by N matrices A. So the special means the determinant A equals 1, and then you want it orthogonal, which means that the inverse is its transpose. In other words, the fact that A transpose A equals 1. And that gives you another example of a Lie subgroup. Okay, so we've looked at the notion of sub-objects for Lie groups. What about the notion of quotient objects? Well, fortunately, we have a nice theory of quotient Lie groups. I won't go through the whole of it, okay, but I'll just briefly indicate some good examples that we can get that way. Okay, so we'll start with this proposition where we have a Lie group G, okay, and we'll have a normal subgroup, so at least we can form the quotient group G mod N, okay, but of course we want this to also have a manifold structure, this quotient group to have a manifold structure which is compatible with the group multiplication. Well, the thing is, if this normal group is actually a discrete subgroup, then G mod N is naturally a Lie group. In fact, you can generalize this a bit more, not to just discrete subgroups, but also to closed Lie subgroups. But I won't really talk about that at all today. Okay, so let's have a look at the case of a discrete group and look in some examples how that works. Okay, so the first one here is a very, very simple example, and just to show you what's going on. Okay, so the groups that are involved are firstly the reals, okay, so that's R to the 1 that I mentioned before, okay, which we saw was a Lie group. And the next one here is basically the circle group. Okay, so what's that? It's just the complex number Z with modulus 1. Okay, so of course this forms a subgroup of C cross, a multiplicative group, and that's called S1. And we've actually seen this before, okay, this is actually just U1, okay? U1, the unitary group of 1 by 1 unitary matrices, okay? So that's all it is. Okay, so the point is that I'm going to construct from this Lie group here to this Lie group here a smooth group homomorphism. And what's that going to be? I hope you can guess. Okay, it's just T maps to the exponential of 2 pi I times T. Okay, so that's the map. And of course you should know that this sends addition to multiplication, so this is a group homomorphism, and of course this is clearly smooth because you're taking well, you're multiplying, that's T by 2 pi I, and then exponential is also smooth. Okay, so as far as groups are concerned, this is a surjective group homomorphism. So the first isomorphism theorem tells you straight away that as groups you have a group isomorphism of the form R mod the kernel of this map. And what gets sent to the 1 here is, of course, just all the integers. Okay, so if you do that, what you'll find is that R mod Z as a group is just isomorphic to S1. And I haven't told you what the manifold structure is here, but I hope you can see, you can believe that whatever manifold structure, it should be compatible with this one here. So since this is smooth, you'd expect this to be an isomorphism of manifolds as well. And in fact, that's the case. So this is actually an isomorphism of Lie groups. And this is the quotient Lie group of R by this discrete subgroup Z. Okay, so this is an example where we have a normal subgroup. In fact, this is commutative, so all subgroups are normal, but this is also discrete inside here. You can form this quotient, and this quotient happens to be something that we've seen before, S1. Okay, so that's all very well and good, but I want to give you an indication of why there is a manifold structure on here. So what I want to do is I want to up this one dimension, and I want to look at R2 mod Z2. Okay, so you can do this the same way as we've done here to see what this is, but I want to show you basically how you get, in general, this manifold structure on a quotient group, at least in the case when n is a discrete subgroup. Okay, so hopefully you can guess what this has to be if you haven't seen this before. Of course, this is the usual torus, so two-dimensional, and one way to see this is you can just take the, this is the product of R mod Z by R mod Z, so it's the product of S1 with S1. Okay, but let's see directly how would we do it if we were trying to do it in general. Okay, so that's the point. Okay, so let's look at the direct construction. Okay, so firstly, as a group, we know what it is. That's all fine. So the group structure is there, and we just have to give a compatible manifold structure. Okay, so let's look at the manifold structure. We need to create charts. Okay, we need to talk about its differential structure. Okay, so what we're going to do is we're going to pick an element of this. So that's a coset. So we can pick V inside R2 and look at its coset V plus Z2. So that's a lattice of dots. I've only drawn 6 of the infinite array of dots. Okay, but so it'll look something like that. That's how you imagine it. Okay, and so what we're going to do now is we're going to draw a open neighborhood of this V, which is small enough so that when you translate that open neighborhood by all these lattice vectors, okay, they will be disjoint. Okay, so that's what we want. So we're going to pick an open neighborhood UV such that if you translate by any lattice point, so m and n here are integers, can you translate this UV by mn? Okay, this translate will not intersect this UV. The intersection will be empty, in other words. So this UV will be something like this. It's going to be a little open neighborhood of that, and when you translate it, it doesn't matter how you translate it, this will be disjoint from all the translates, and so by symmetry they'll all be disjoint from each other. Okay, so that's the UV, and also when you've added all possible Z2s to it. Okay, so why have I done that? So let's have a look and see. Okay, so let's look at the quotient map, which is the way you want to study quotient objects. Okay, so let's remind ourselves of this quotient map. Okay, that goes from the original object R2 to the quotient R2 mod Z2, and that just sends an element, say W, this 2 tuple of reals, to the coset of Z2. Okay, so it sends it to the coset. Okay, so let's pick a W inside here, W. And the coset would be, well, you look at the corresponding, all the translates. So it'll be like this, 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 and this. Okay, so it'll be that coset of black dots. Okay, so that's the image of W inside the quotient space. Okay, and what we're going to do is you have this, it's quite a complicated sort of a thing, but what we can do now is we can restrict this quotient just to this small open neighborhood of V. Okay. You restrict to the small open neighborhood of V, and what do we notice about what's going on here now? Okay, what we notice is that whereas before, of course, this is many to 1. This is Z2 countably infinite to 1. Okay, so to any point here, you have a whole coset of Z2 inside there, so it's Z2 worth of things mapping down to 1. But when we restrict it to this small open set, actually, it's going to be 1 to 1. Okay, so in particular, if you look at just the image of pi UV, this will be an isomorphism, at least of sets, and in fact, topologically, it's going to be an isomorphism, in other words, a homeomorphism. Okay, and you can see this from this picture. If you have any 2 elements inside here, right? Okay, if they have 2 elements inside here, then they get mapped to different elements. If they got mapped to the same element, that means that they have to be an integer apart. But the things, so basically they have to be in the same coset of Z2, but all the things that are in the coset of W, they're these black dots, which are in different blue triangles, okay? So they're different translates, okay? So all the things equivalent to W are all these other black dots, okay, all the other things in the coset. And so in particular, none of the elements inside this UV here, none of the elements inside that UV get mapped to the same place as W does under this thing here. So when you restrict to UV, this is actually injective, and by the theory of quotient topologies, okay, this is actually going to be a homeomorphism, okay? So you get this homeomorphism. Okay, so why did I do that? Okay, so in particular, you have a homeomorphism, and pi of UV is going to be an open neighborhood of pi of V. So pi of V, so V was anything inside R2, pi of V is inside the quotient, and now we have an open neighborhood of that, and we want to put a differential structure on that. And what we do is, well, we have a differential structure on UV because this is an open submanifold of a manifold. Okay, so we can talk about charts there, and just restrict those charts to here. Okay, just use this homeomorphism to induce charts over here instead. Okay, and if you work slowly through the details, you'll actually see that this does actually define a manifold structure on here. Okay, and it defines a manifold structure such as this map here. Pi, when we stick to UV, is going to be a diffeomorphism. Okay, you insist that these are diffeomorphisms. Okay, so it turns out that this not only defines a manifold structure here, but I hope you can also see that since the group, in this case addition, is smooth and the negative is smooth, the same actually will be true over here. Okay, and that's a fairly elementary sort of exercise once you know how this theory works. Okay, so that's great. So that shows you the general principle of how you construct the Lie group structure on a quotient, at least when that normal subgroup is a discrete subgroup. Okay, so I want to make some very, very interesting remarks about this situation here. Okay, so the first one is the following. Okay, so suppose you have this Lie group and you have a normal subgroup which is actually discrete. So the first thing that in general, G to G mod n, this quotient map, just like in this example here, is a local diffeomorphism. Okay, you can always find this UV and construct the manifold structure this way. So this is going to be a diffeomorphism, and that means that this projection is a local diffeomorphism. Okay, that's rather nice. And if it's going to be a local diffeomorphism, that means it's at least a local homeomorphism. So this is actually a covering space. So if you're familiar with this theory of fundamental groups and of covering spaces, this shows that this is actually a covering space. Okay, and in fact, the deck transformations, the group of deck transformations, is given by this discrete group n here. Okay, so the other thing you'll see is that that this G mod n, it's actually topologically more complicated than the original group G. Okay, so let's just see what that means. This is an imprecise statement, but we can look at the examples and kind of see what this means. Okay, so here you have this R. Okay, so in what ways is it very simple topologically? Well, this is simply connected. Okay, so any loop that you have inside here, you can contract to a point. Okay, it's in fact a contractible space. Okay, but the same is not true of this quotient R mod Z. Okay, what is the quotient of R by the Z here? Okay, when you take that quotient, it's going to be this circle. Okay, so this circle is not contractible. In fact, it has a non-trivial fundamental group, and the fundamental group is actually Z. Okay. So in fact, this R is the simply connected cover of this S1. And a similar thing happens here. Okay, you look at this R2, this is contractible, this space, but this R2 mod Z2, it's the torus. Okay, so topologically, it's much more interesting, okay, and complicated. So that actually is a general phenomenon that we see. And what this last result that I want to tell you about, and a really, really interesting result is that, well, if you take a quotient and it gets topologically more complicated, can you undo the quotient and make it as simple as possible topologically? And the amazing thing is that you can actually do this, okay? So the next result sort of reverses this. You want to undo a quotient, okay, where you may not see what that might be, okay? So you want to undo the quotient to get the topologically simplest possible, okay? And this is the way to state the result, okay? So the proposition involves a Lie group G, okay? And what we do is that we consider its simply connected cover, okay? So that's some topological space, G tilde, okay? together with a quotient map like this. And this is going to be a covering map such that this is simply connected. Okay, so its fundamental group is trivial. Okay. So in this case, what happens is that you can actually make this essentially a quotient of Lie groups. So in fact, you can put a Lie group structure on this. So you can firstly put a group structure on this, and also a manifold structure on this. The manifold structure is not so difficult because this is a manifold, okay? Such that this is a Lie group. And in fact, moreover, this quotient map is going to be firstly a local diffeomorphism, and secondly, it's going to be a group homomorphism. Okay, so that's rather nice, is that you can sort of undo the quotient procedure, even though you don't see what this is. So if this is not simply connected, okay, you can undo this. Okay, and basically this G will be G tilde modulo the fundamental group. That's going to be how it works. And just to give you an indication of how this sort of theory works, okay, why this is true, okay, if you want to see. And perhaps the most interesting thing is to see, well, what's the group structure here? Okay, so suppose you have G is here, okay, and then what is it simply connected cover? Well, I guess you can pick a base point. Okay, so maybe I should do this for a connected Lie group. But I guess this is not a big deal, okay. And what's one way to form it? Simply connect cover. I guess one way to do that is that we pick a base point. Maybe the natural one here will be just the identity. And you look at homotopy classes of paths from here to say G. Okay. So of course there's a natural map from here to G. You look at the endpoint where that is. And now we need to say, well, if you have two of them, two homotopy classes of these, so we have another one maybe going like this to say H, how do we multiply them together? Okay, so we need a homotopy class of paths from 1 to something, okay, and it should lift so that you have the multiplication, okay. So what you can do is you can take this G and you can, since you're in a group, you can translate this path by G. So that's a translation of the path to GH. Okay, and that gives you a path now to GH. That's defined up to homotopy. Okay, and that's going to be your new element of G tilde. And to see that you have a group homomorphism, okay, so where does this end up? When you map the product of these two paths, or equivalence classes of paths, you get map this over this way. Of course, you get just G times H, and that's what you wanted. I hope you enjoyed this adventure in pure mathematics.